Well, welcome back. Today we've got a slightly more challenging lesson to deal with today. We're going to start working on decoding information about chemical equations and learning to write them out in word form and then in symbolic form. So this is definitely a little bit more challenging than 4 signs of a chemical reaction. So yeah, wake yourself up, get yourself your snack, whatever you got to do, go to the bathroom, and we'll get started here. So this is all about, like I said, learning how to write chemical reactions in word form and then in equation form, at least to start. So first of all, we've kind of talked about this before, but just in case, to review, chemical reactions, we get something new that's being produced. We have to have a way of describing sort of what's going on in this reaction. We have to have a way of representing what was present before the reaction, as well as what now is present as a result of the reaction. So we have to have some sort of kind of typical things that we do all the time to represent those things. This symbolic representation, it kind of looks like a math equation almost with letters in it, more like algebra, I guess, is what we call a chemical equation. A chemical equation is just a symbolic way of representing what's going on in a reaction. The reaction itself is obviously the chemicals together in a beaker doing something interesting. The chemical equation is what we would write on the piece of paper to sort of record what was happening as a result of that. So first things first, we need some vocabulary to discuss these things. So the things that are present before a reaction, like over here on the screen, we've got this piece of wire, and then we've got this clear solution. That's kind of the before chemicals. We would call those reactants. Reactants are things that are going to react together but necessarily haven't yet. There's always at least one reactant, but you can have 2, 3, 4, any number of reactants that would come together in a chemical reaction. A lot of the ones that we deal with are going to have 1, 2, or maybe 3 reactants. Then on the other side of this reaction, the after part of it, we've got something that's been created. So that's kind of in this particular screen up here, so this blue liquid is now the stuff that's been produced. Well, we would call that a product. Kind of makes sense. Products are produced after a chemical reaction, so it's kind of the after stuff. You have to have at least one product, but again, you can have 2, 3, 4, or more than that. And then most of our reactions that we're going to deal with are going to have 1, 2, or 3 different products. They don't have to equal one another. You don't have to have the same number of products and reactants. So for example, in this one, it kind of looks like there's 1, 2 different reactants and 1 product. So they don't have to be equal. So just kind of keep that in mind. So reactants go in, products come out. When we're writing chemical equations, we have a similar sort of set of rules that we use. So for example, reactants are always on the left. We always start with reactants on the left side, and we sort of add them together. We use a plus to indicate that if there's more than one reactant that's present. It does not matter which side we would put these two on. So I could have put the O2 first and the H2 after. That's totally acceptable. And then we have the products. What's come afterward is ending up on the right side of this thing. And again, if we had more than one product, we would use a plus sign, just like in a math equation, to say that there's more than one different kind of product that's there. And then the third thing that we have in a chemical equation or chemical reaction is an arrow of some sort. And the arrow kind of tells us the direction that the reaction is proceeding. For what we are doing right now up until almost the end of class, your arrows will always point to the right, and that kind of indicates what we would call a forward reaction, where we've got 2 reactants coming together and then sort of equals, but not really, creates a set of products that's on the right side. So those are the 3 basic things. Reactants on the left, then there's an arrow, and then there's products on the right. And again, with our reactants, you have a plus if you've got more than one kind of reactant, or a plus if you have more than one kind of product, and that's totally fine. So one of the key things that we have to keep in mind when we're writing chemical equations is the law of conservation of matter. You may have heard of it called the law of conservation of mass as well, and they're both basically the same thing. This is that idea that matter cannot be created or destroyed in chemical reactions. It can be in nuclear reactions, but that's a different class. So in our normal chemical reactions, that means that the products that we have, this new stuff that we're creating, isn't actually new at all. It's consisted of the exact same atoms that were there to start with. We've just sort of rearranged them. I kind of think of it as like I had a Lego car that I built, and then I disassembled my Lego car, and now I built a plane out of it. The Legos themselves are exactly the same. It's just the way that I bonded them together, the way that I assembled them is what makes the toy, I guess, look different when you're done. So it's important here that when you're writing chemical equations, that the reactants and the products have to contain exactly the same elements. You can't have an element appear or disappear during a chemical reaction. So whatever elements are present on the left, those elements have to be present on the right, although we can recombine them in different ways. So for example, a log is actually mostly carbon, hydrogen, and oxygen. They're bonded together in the form that we call wood, which is cellulose and a variety of other things. But when we burn it, the two things that we produce, which is carbon dioxide and water, contain those exact same three elements: carbon, hydrogen, and oxygen. So whatever's there before has to be there after. No appearing and disappearing elements. That's not allowed. So here's what this looks like when we're starting to apply this idea to writing chemical equations. Basically, if you know what's on one side, you have to know what's on the other side. It's just going to be a matter of rearranging. And at first, you won't have a lot of knowledge for kind of how they're going to be rearranged. But when I take a look at this one where I've got A, B kind of bonded together and C by itself, I have an idea that maybe they're going to all come together and form one big product, maybe an ABC, or maybe one of them is going to switch places. So for example, in this case, the C kicks out the A, and you have a slightly different compound that's formed. Still the same three elements, just a different arrangement of those three elements. And this one on the bottom down here is more, kind of that same idea. If I've got these as my products, I know those had to come from somewhere. If I've got those four elements in the products, they had to come from the four elements as reactants. Maybe they were four single atoms, maybe they were two different compounds, maybe something else. And in this particular case, I had just a switcheroo of who was dancing with who, so to speak. But again, that idea of conservation of matter means that whatever elements are present on the left are present on the right, and vice versa. So if you know one side, it helps you start to be able to predict what's going on the other side of the reaction. This also goes a little bit further for us. Not only does the number of elements have to be conserved, but the number of atoms of each element that's being reacted also has to be conserved. So I can't say like 2 atoms went in and all of a sudden magically 5 atoms came out. We don't get to just create and destroy atoms on there. So unfortunately for this kind of goes more into the next lesson, but this means we have to actually balance equations where not only do we show the same type of elements on the left and the right side, but we have the exact same number of elements and number of atoms on the left and the right side. So for example, this one I've got a picture of here is the reaction of combustion of methane, which is basically natural gas. So if I have CH4, which is methane, and oxygen gas, I know I'm going to be producing two things, which is carbon dioxide and H2O. So we've got our reactants over here on the left, and we have our products over here on the right. You can see our arrow in the middle that shows our direction of reaction. Again, I could have written these two in reverse order. I could have written O2 plus CH4, that's fine. And I could have written CO2 plus H2O or H2O plus CO2. That's also fine. Doesn't matter. You can swap the two. You just can't switch the sides. Whatever's a reactant has to stay on the reactant side. So, oops, I'm going to go back, sorry. So I can see here that my conservation of matter is good on the one hand, where I've got the same elements on both sides. I've got carbon, hydrogen, and oxygen. No mystery aluminum appearing or disappearing or something else. But this particular equation, as I've written it, isn't quite fully conserved. I've got the right elements, but I don't have the right number of atoms. And you can kind of see that that's what this little accounting thing is down here. I've got one carbon on the left, and there's still one carbon on the right, so that's fine. But somehow 2 of my hydrogens have magically disappeared. I started off with 4 hydrogens, but only 2 of them are shown up in the products. And then somehow magically an oxygen has appeared. I started with 2, and now I have 3. So all that means is that I have to do a little bit of work to balance my equation. So we'll see what that looks like here for the most part in the next lesson. So I said for right now, law of conservation of matter, elements on the left have to equal the elements on the right. And in the next lesson, I'll teach you how to keep the atoms on the left to equal the atoms on the right. So when we do this, we're going to use something called coefficients. I'm just going to kind of give you a heads up into what these things look like. Coefficients, we've seen them before actually earlier in our year, but it's a number that we put out in front like this. There's one in front of the O2, and then there's one over here in front of the H2O. What this actually means now and how I balance my equations is it's not really one oxygen molecule that was associated with this reaction. It was actually 2 of them. I had an O2 and a second O2. And then the same thing on my product side. I didn't just make 1 water molecule. I ended up making 2 water molecules. And this is, like I said, more about the next lesson, but this is kind of how we go into this process. To accurately represent what's really going on, how these atoms are being built and then rearranged, we have to sometimes use these coefficients to say, okay, it isn't just 1 CH4 and 1 O2. Maybe it's a different combination of things that are coming together to make everything kind of work out perfectly. So again, this now, as shown, is perfectly shows the law of conservation of matter. We've got the same elements on both sides, and we have the same number of atoms on both sides. We have 1 carbon on each side, we have 4 hydrogens on each side, and we have a total of 4 oxygens on each side. I said more on how to do that in the next lesson. I just wanted you to know that it's one of those things we do have to kind of watch out for. Okay, so stuff that's contained in chemical equations. What kinds of things can you get from this? There's a variety of things. We've already talked about the identity of the reactants of the products, that there's chemical formulae in there, so we can kind of know which elements are present and what the formulas of each compound is. We'll also know that when it's balanced, at least how many molecules of each are involved by using coefficients, so like 2H2O or 2O2. A lot of times in chemical equations, they'll also include important information about the physical state, whether it's a solid, liquid, gas, or a solution. There's something called an AQ, or an aqueous solution, means it's dissolved in water. It's different than being a liquid, so we have to be really careful with this. So like, for example, salt. If you have a solution of salt water, that's different than melted salt. You've never actually seen melted salt because it takes like 800 degrees Fahrenheit or something like that. I can't even imagine trying to melt salt crystals. But dissolving it in water, it kind of looks like a liquid. It's not actually the liquid form, not solid liquid gas, melted, frozen kind of solid liquid gas, but dissolved in water has a different connotation for us. And it is important, we'll practice this in class. But it's actually solution is what we'd use for that, and that's represented with an AQ. Next piece for you is to keep in mind that a lot of our gases that we're going to deal with, our elemental gases, are what we call diatomic. In other words, they never exist as a single atom of, say, hydrogen or nitrogen. They're always in pairs, kind of like having a pair of socks. These are called diatomic because di means two and atomic means atom, so these are two atom gases. Easy way to remember these is the silly word Hanafkelberry. H-N-O-F-C-L-B-R, Hanafkelberry, or Hanafkelbrie if you prefer, if your name is Brie. But those are our diatomics, so every one of those common gases right there always exists as a two form, H2N2O2. Fluorine and chlorine and bromine do the same kind of thing. And then the last thing, a lot of times in chemical equations, they'll show you something about energy. I'm not sure why this is still on here. That's kind of interesting. But there's no equation on there. But energy change of a reaction where heat is absorbed or released, sometimes that is included in a reaction as well. So here's some examples of what this looks like. Unfortunately, it'd be so nice if they were always given to you, but the whole point of this lesson is you have to write out the chemical equations a lot of times. So here's a story of something that one of you might possibly do. A curious chemistry student like yourself finds a little slice of magnesium, decides to drop it into some hydrochloric acid that was just apparently sitting around. I don't know why your chemistry teacher would do that. Very irresponsible. Very. But as you watch it, it starts to fizz, and it slowly kind of disappears after a little while. You touch the beaker and you realize it's warm. Like, that's kind of weird. And the metal is completely gone. So you start off with a chunk of metal and the stuff that looks like water. It's hydrochloric. And then at the end, you have, again, a glass now of clear water, or clear liquid. It's not really water. And it's kind of warm. And so then the question is, what did you create? The teacher says, oh, look, you made some magnesium chloride, but what was the gas? So this is how you would start to attack a problem like this. The question of prompt would be like, write a word equation and a formula equation for this reaction. Yay, great, shoot me in the face, right? Anyway, so how do we deal with this? Number one, first thing in your head, try to picture what's going on. I've got a beaker, I drop some metal in it, it's fizzing around, and then after it's okay, now I have this kind of warm beaker. It helps if you picture what's going on in the system. Number two, try to look for word clues. What are the reactants and what are the products? What was there when you started, and then what was there when you're done, and what did they look like? The third thing is look for missing elements, just in case something is kind of left out, like in this case, what gas did you create? There's a hint that there's a missing element in there somewhere. And then you have to actually start writing the formulas out. This is using some of your old chemistry formula rules, so you have to balance your charges and all that kind of stuff. So let's take a look at how this one works out. So here I've highlighted some of the key words from this particular thing. So I'm looking for reactants and products, and I'm looking for my kind of starter word equation here. So I know that magnesium metal was there when I started, and I had hydrochloric acid when I started. That's what I began with, and then something happened. It started to fizz. It started to kind of slowly disappear, and then when it was done, I have this warm, kind of clear solution with apparently nothing else in it. And then the teacher says something about magnesium chloride. So what's actually going on here? So I've identified my reactants. I've got magnesium metal and hydrochloric acid. I've got products, at least I know something about magnesium chloride. And then I know I have a missing gas. So that missing gas is the fizzing. So I don't know what that one is, but I'll be able to figure it out. And I started to write out what my word equation would be. And so here it is. It's not balanced. It's not quite done yet. But I've got magnesium plus hydrochloric acid, or you could write hydrochloric acid plus magnesium. And then I have my reaction arrow. And then I've got magnesium chloride, because I know that's something I produced. And then some sort of gas. And then some sort of heat is also produced. I know it's produced because it gets hot at the end. Okay, well, I'm back. Sorry about that. I had to hit pause because I got interrupted by a bell ringing and a variety of other strange things happening. So hopefully this will go back together. So we're going to take our little reaction word problems that we had on the last page just a little bit further. Here's where we have to go and start translating it from word problems to formula problems. And this kind of helps us figure out what we might be missing from our reaction. So here's what we started with: magnesium and hydrochloric acid was going to form magnesium chloride, some sort of gas, and heat. So when we do this, start writing out the formula. So magnesium is just Mg. It's an element all by itself. HCl is hydrochloric acid. And you may or may not remember that, and that's totally fine. And in this case, I've left out the physical states just so we can kind of focus on writing what the actual formula is, so don't stress about it too much that I didn't put those pieces in there. All right, so what do we have on the other side? Well, we have on the other side magnesium chloride. Here's the hard part. Whenever you're writing products or formulas for products, don't forget you still have to go back and balance charges. So magnesium is a 2+, check your periodic table. Chlorine is a 1-, so that's why it's MgCl2 by the time you're done writing it. So don't forget to go back and actually balance your charges. We have some sort of mystery gas, and then we have heat. So how did I know the mystery gas was H2? Well, if I take a look at law of conservation of energy from this, what do I have in my first half of my equation, my reactants, that I don't have in my second half, which is my products? So the magnesium and the chlorine are both present over here in the MgCl2. So that means that the hydrogen must have gone someplace. And again, this is one of those kinds of reactions where that last element has to be accounted for. It's got to be the gas that's coming off of here. And in terms of this, you'll have a little bit more practice with recognizing these. So I'm sure it's probably not super obvious where that came from. The other part of this is that it is H2 because it's a diatomic gas. It's one of those few gases that we talked about earlier in the year. We'll come back and visit these again. That when you've got hydrogen in its elemental form, it's always H2. It's always two hydrogens sort of holding hands, so to speak. And then I put heat there as one of my products to it. So again, a little bit different in terms of how it's finally reacted. That's what it would look like all together with my physical states. Magnesium was a solid to start with. The HCl is a solution that's not liquid hydrochloric acid. That would be just frightening. So that's hydrochloric acid solution. And then on the right, we've got magnesium chloride solution. That's why it's AQ for aqueous. And it was hydrogen gas because it was fizzing. And then we had energy left over. So this is an unbalanced equation, but this at least shows law of conservation of matter for the different elements that are present in there. Okay, so just to review what we've got to do when we're doing these. So number one, reactants are always on the left, and then there's an arrow, and products are always on the right. Have at least one reactant, but there can be more than one, and at least one product, but there can be more than one. We always have to take advantage or take into account the law of conservation of matter, and that in the end tells us that we have to have balanced chemical equations. At first, for right now, you're going to make sure they're balanced in terms of the number of elements that are present, so any of the elements that are present in the reactants have to also be present in the products. And then in the next lesson, we'll learn how to balance equations to make sure they're balanced in terms of the numbers of atoms, not just the number of elements. The third hint here when you're writing out chemical equations is that you have to use some clues from either the story or the problem or the lab or whatever it is to get some clues as to which things are reactants and which things are products. You're going to look for things like react to form, decomposes, breaks down into, produces, little word clues that are going to be kind of hidden in there. So you have to sort of read carefully and use a little bit of imagination, I guess, to figure out what's a reactant and what's a product. There's also maybe going to be some clues in there about the physical states, like whether they're solid, liquid, gas, or most likely if they're going to be aqueous, which means they're in solution. And then you might have some word clues, sometimes not, about energy. Energy had to be put into it, it was lit on fire, something like that, or it was energy given off to it, like it got hotter or something along those lines. And then the last thing is to keep in mind there's two different kinds of equations we're getting out of this. We're getting word equations, which is starting off with just the names of the compounds, and then we also get formula equations coming from there, where we're actually starting to write the actual chemical formulas with balanced charges and subscript numbers and parentheses and all that kind of scary stuff. So sometimes it helps to start with a word equation, and then start translating it into the formulas, because the formulas is where we're going to need to go by the time we're done. So there you go, representing chemical reactions in terms of how do we start to write out basic chemical equations. Hope you enjoyed it, and I'll see you in the next one.